There are places in the sky, where the ancient light from the dawn of time seems colder than it should be. In the year 2004, astronomers were poring over the data from a remarkable probe, the Wilkinson Microwave Anisotropy Probe, WMAP. Its job was to listen, really listen, to the faintest, oldest whispers of the universe, the cosmic microwave background radiation. Think of it as the afterglow of creation, the very first light, stretched and cooled over 13.8 billion years into a faint, pervasive hum of microwaves. And this hum is astonishingly uniform, the same temperature almost everywhere we perceive. But not quite. In a vast swath of the sky, in the direction of the constellation Eridanus, they found an anomaly, an immense patch of space that was profoundly, inexplicably colder than the average. It became known as the Eridanus supervoid. The sheer scale of it, well, it almost defies imagination. To get a sense of its staggering emptiness, you could line up something like 20,000 galaxies the size of our own Milky Way, end to end, just to cross it. And remember, light itself, the fastest thing there is, takes 100,000 years just to get from one side of our galaxy to the other. The implications of this cold spot were immediate, and they were profound. Of all the explanations that were floated, one resonated with a kind of poetic grandeur. The idea that this cosmic anomaly might be an imprint, a residual echo of another universe. A universe that perhaps bumped into ours, or branched away from it, right at the beginning of everything. A subtle, yet monumental scar on the fabric of our existence. A relic of a fundamental cosmic divorce. And then, just 4 years later, in 2008, something else emerged from the data. A team led by an astronomer named Alexander Kashlinsky presented evidence of a vast coordinated movement of at least 1,400 galaxy clusters. Now, these aren't just galaxies. They are colossal collections of hundreds or even thousands of stellar islands, all streaming together in a unified direction towards something beyond the edge of our observable universe. This was, to put it mildly, astounding. According to our standard picture of the cosmos, the motion of these great clusters should be largely random, a chaotic dance governed by local gravity and the overall expansion of space. But here was a grand, overarching current, an unseen river of galaxies. They called it the dark flow, not because it's visually dark, but because, like dark matter and dark energy, its fundamental cause is completely unknown to us. The name is an admission of our own ignorance. The findings were so unsettling that Dr. Kashlinsky himself said with remarkable candour that they just didn't have enough information to say what this force was. All they could say for certain was that somewhere, very far away, the universe is profoundly different from the little patch we can directly apprehend. A different universe, perhaps, a distinct manifold of space-time. The question hung there, tantalizing and unanswered. The feeling was palpable. We were on the precipice of something entirely new. And now, fast forward to our time. Just recently, an article in the journal Nature presented yet another challenge. Using the James Webb Space Telescope, astronomers detected 6 celestial objects that, according to everything we think we know, simply shouldn't exist. You see, the Big Bang happened about 13.8 billion years ago. These new objects seem to have formed a mere 600 million years after that. That's incredibly early, in the universe's infancy, a time when conditions were thought to be far too nascent for such massive structures to form. We're talking about 6 enormous galaxies, whose very existence in such a young universe just confounds our models. The theories say that galaxies back then should have been at least 10 times smaller, maybe even 50 times smaller. There just shouldn't have been enough ordinary matter available to build these stellar cities so quickly. One of the lead authors, Dr. Erica Nelson, put it starkly. She said that if even one of these galaxies turns out to be real, it would fundamentally dismantle our current understanding of cosmology. It's that serious. No definitive explanation has emerged yet. But among the more whimsical suggestions is the idea that perhaps we need to introduce a concept of dark time, some unknown influence that accelerates cosmic development. Such playful speculation just underscores the profound bewilderment, the urgent need for new paradigms. Have you noticed the theme here? A consistent refrain woven through each of these discoveries. In every case, the same phrase echoes. This discovery has called into question the fundamental postulates of our cosmological model. It's a testament to the self-correcting nature of science, but also a stark reminder of how provisional our knowledge is. If all these observations are confirmed, if they aren't just glitches in our methods or errors in our calculations, then we are, without a doubt, facing a crisis in our theories about the cosmos. And here's the crucial point. That is profoundly good news. A crisis in science isn't a disaster. It's the necessary precursor to a revolution. It signals the limits of an old way of thinking and forces us to forge new tools, to expand the very boundaries of human understanding. It's in these moments of intellectual discomfort that science truly leaps forward. And yet, despite these profound anomalies, cosmologists continue to write the word universe with a capital U. The emphasis isn't just grammatical. There's a deeper philosophical implication embedded in that capitalization, a subtle presumption that we've grasped the ultimate nature of things, even as the cosmos continually presents us with riddles that defy our most sophisticated frameworks. You see, a short while ago in the quiet of a late night, as is often the case when these profound questions surface, I was gripped by this overwhelming desire to comprehend what, theoretically, might lie beyond the very boundaries of the universe. I found myself pondering the most fundamental of inquiries. Does such a boundary even exist? Is there a literal edge we could, in principle, approach? What would happen if you just embarked on an endless journey, continually moving in a single direction? Would you ever reach a termination point? And if you did, what form would it take? A collision with an impenetrable obsidian wall, or would you pass through it? And if so, what realm, what unimaginable expanse would greet you on the other side? Now, for those who might dismiss such questions as naive, I urge a moment of reconsideration. This question has captivated and tormented humanity's most astute minds for millennia. A huge part of historical cosmology was tied up in notions of a discernible centre and an ultimate edge. There's a fascinating 19th century engraving that powerfully encapsulates how people in the medieval period might have conceptualized this. It depicts a traveller pushing through the celestial dome, breaking past the firmament to glimpse a hidden, intricate mechanism, a grand clockwork perhaps, that governs all of creation, lying just beyond the veil of our perceived reality. It's a potent reminder that this quest is as ancient as our capacity for wonder itself. Driven by this nocturnal quest, I plunged into the vast ocean of online information. What did the wise people have to say? To my initial dismay, I discovered a striking homogeneity. Almost every article, every video seemed to adhere to a depressingly similar template. This common structure was perfectly, almost ironically, articulated by a trenchant comment I found on a forum beneath yet another article titled, "What does the edge of the universe look like?" The comment succinctly summarized the prevailing narrative. First, talk about the Big Bang, then talk about it again and again. Finally, subtly substitute the phrase edge of the universe with edge of the observable universe, profit. And indeed, this pithy observation captured my frustration perfectly. It is, of course, a well-worn truth that if we were to use immensely powerful telescopes to peer to the farthest reaches of space, we wouldn't perceive a literal spatial edge. What we would apprehend is its temporal beginning. The reality of light travel time. When you're talking to someone at a nearby table, you're actually perceiving them as they were a minuscule 3 nanoseconds in the past. When our gaze falls upon a distant star, like Betelgeuse, we are beholding it as it existed about half a millennium ago. For all we know, that colossal star might have already ended its life in a spectacular supernova, its light still travelling towards us, a message from the past. Even the Andromeda Galaxy, currently hurtling towards our Milky Way at around 400,000 kilometers per hour, is, for the same reason, actually a full 900 light-years closer to us than its current light image suggests. And 900 light-years is an immense distance. For context, the closest star to our Sun, Proxima Centauri, is a mere 4.24 light-years away. Yet even with our best technology, a journey there would take tens of thousands of years. The fundamental point is clear. We can't perceive a distant object in real time. The farthest point we can observe is the location from which light has had just enough time to reach us since the Big Bang. This conceptual perimeter defines the boundary of the observable universe, and it was precisely this boundary that held no interest for me. Why? Because it's almost certain that beyond this visible horizon, the cosmos continues its boundless, enigmatic sprawl. I was seeking a genuine physical boundary, or at least a compelling theoretical construct that could serve as intellectual sustenance. And eventually, after a protracted and circuitous exploration, I did indeed find something to ponder. The journey led me to the profound insights within a particular book, Cosmology, The Science of the Universe, by Edward Robert Harrison. And from its meticulously crafted arguments, a startling realization began to crystallize. It's entirely possible that my very question about the edge of the universe might be fundamentally misconceived. Even if such a boundary were to exist, and even if we were to arrive at an understanding of it by the end of this contemplation, the nature of that understanding might be far more subtle and profound than a simple spatial frontier. The book itself is a venerable work, and its author has long since passed from this realm. Yet, his legacy endures. He was a distinguished professor of physics and astronomy at the University of Massachusetts, a scholar whose achievements are too numerous to fully list. Harrison was an exceptionally well-read individual, captivated by the grand sweep of intellectual history. He consistently interwove references to poetry, classical history and philosophy, masterfully employing them to illuminate the abstract tenets of physics for the uninitiated. What truly impressed me most was his unhesitating willingness to delve into the most bottomless, philosophical questions that arise from our understanding of the cosmos. At the conclusion of each chapter, he would engage in a shared reflection, posing thought-provoking questions that transcended mere factual recall. This wasn't like the perfunctory check-your-knowledge sections of a textbook. It felt much more like an intimate conversation with a trusted friend, late at night, where the fear of appearing ridiculous completely dissipates. For instance, he'd present an idea and then gently inquire. Many people, such as materialists and reductionists, overwhelmed by the sheer grandeur of the physical universe, believe that whatever is not contained within it simply does not exist. What are your thoughts on this? And there you sit, reflecting on the startling audacity of such a question in a formal academic discourse. It challenges the very boundaries of conventional scientific inquiry. To my regret, this seminal work has not been translated into my native language, but it is readily available in English. Returning now to that 19th century engraving, we might, from our modern vantage point, indulge in a sense of smug superiority about the naivety of past beliefs. We might muse on how far we've advanced. However, as Harrison's insights gradually reveal, it is highly probable that, in terms of fundamental conceptualization, we may never truly distance ourselves significantly from the perspective of those individuals from the medieval era. The more deeply we probe, the more acutely we may realize that our models, however sophisticated, still grapple with the same fundamental enigmas, albeit dressed in new scientific garments. This realization will, I trust, become increasingly evident as we continue our journey. So, where did this quest of mine truly begin? Initially, I decided to confront the problem head-on. I posed a thought experiment. What would happen if one were to assemble a vast contingent of individuals, settle them aboard an immense starship, and dispatch it in a single, unyielding direction with the explicit mission of reaching the ultimate edge of the universe? And what if this vessel were designed to accelerate at the maximum possible rate? An expansive and utterly captivating response to this very question was offered by the esteemed astronomer David Kipping of Columbia University in a half-hour video presentation. It's a highly recommended resource if you have an ear for such things. Let us then, for the sake of our mental expedition, imagine this starship. It can accelerate indefinitely at a constant rate of 10 meters per second. Beyond the thrill, this constant thrust would confer a practical benefit. The passengers would experience a sensation akin to normal Earth gravity. You might recall that Earth's gravity is approximately 9.8 meters per second squared, so our ship's acceleration is conveniently close to this familiar sensation. To visualize the accumulating speed, in the first second, the ship would attain a speed of 10 meters per second. In the second, 20 meters per second, and so on. After just 1 hour, the ship would be moving at an astonishing 35,280 meters per second, and the acceleration would continue unabated. For this thought experiment, we shall politely set aside certain practical inconveniences. We will not dwell on the improbable logistics of fueling such a vessel, nor the insurmountable challenges posed by collisions with microscopic dust particles at such velocities. These are mere trifles when weighed against the grandeur of our cosmic quest. After a mere 2.5 hours, our starship would have hurtled past the Moon. In just 1 week, it would sweep past the rings of Saturn, and a mere 11 days into its journey, it would leave Neptune far behind. Yet, it would be a full 15 months of continuous travel before the ship would traverse its first light year. And it is at this juncture that the truly bizarre phenomena predicted by Albert Einstein's special theory of relativity would begin to exert their profound influence. To begin, the laws of physics do not forbid a ship from accelerating indefinitely. However, a massive object like our starship is fundamentally incapable of actually reaching the speed of light. One can approach this cosmic speed limit with ever-increasing closeness, but the absolute barrier remains inviolable. Consider the protons in the Large Hadron Collider. They are propelled to a speed of 299,792,455 meters per second. One might casually observe that this is just a paltry 3 meters per second shy of the speed of light. 3 meters per second is roughly the speed of a brisk jog. Yet despite this seemingly minuscule difference, the laws of physics dictate that it is an unbridgeable chasm. Even if you were to expend all the energy in the entire universe to imbue that proton with those last, elusive 3 meters per second, it would merely draw infinitesimally closer, achieving a proximity expressed by an endless string of nines after the decimal point, but never, ever quite reaching it. So, were it not for this limit, our hypothetical starship would have surpassed the speed of light in a mere 45 days. However, the reality, as dictated by special relativity, is far more complex. What actually happens is this. The faster an object moves through space, the more slowly it effectively moves through time. From the perspective of a stationary observer, it would appear as though the ship's acceleration gradually diminished. Furthermore, the lives of the individuals aboard would seem to unfold in an ever-slowing motion. Yet, from the internal perspective of the crew, time would continue to flow at its normal rate, and their sustained acceleration would remain constant. Adding another layer of complexity, the crew would observe that, relative to their accelerated frame, time in the external universe had seemingly accelerated. To reiterate, if special relativity were suspended, our ship would have achieved light speed in just 45 days. Yet in reality, after 15 months of continuous flight, it would be travelling at only 87% of the speed of light. The temporal dilation, the slowing of time, follows a highly nonlinear curve. The true, mind-bending extremes only manifest when one approaches the speed of light almost infinitesimally close. Consider, as a striking example, a truly remarkable event that occurred on October 15, 1991. On that date, a single cosmic ray particle impacted Earth's atmosphere. Its energy was so immense that scientists christened it the "Oh my God" particle. This particle was moving at an astonishing 99.999999999999999999999999999999999999999% of the speed of light. But the most staggering implication is this. For that particle, time itself was dilated by a factor of 300 billion, when compared to the flow of time for a stationary observer like us. This means that for us observing its journey, it would have taken approximately 2.5 million years for that particle to traverse the distance from the Andromeda Galaxy to Earth. Yet, for the particle itself, subjectively, less than 5 minutes would have elapsed. This leads to an almost paradoxical conclusion for light itself. For a photon, time, in essence, entirely ceases to flow. It's not that we could say, for a photon, this much time passes, because there are no clocks that can travel at the speed of light, rendering such a statement meaningless. Yet I trust the fundamental principle of this profound temporal distortion has been grasped. Now let us consider the far-reaching implications. It means that interstellar travel at near-light speeds represents a kind of Faustian bargain. If our hypothetical starship were to simply embark on a round trip to the Andromeda Galaxy and return, a journey that would subjectively consume 56 years for the travellers, it would correspond to an astonishing 5 million years passing on Earth. Ponder the fate of human civilization over such an immense span of time. Would you, dear listener, consent to glimpse another galaxy at such an incalculable cost? Furthermore, if our starship were not intended to return, but to continue its relentless journey outward, there would come a point of no return. Upon traversing the threshold of 8.3 billion light-years from Earth, the pathway back would be irrevocably sealed. There is no tangible barrier, yet once that mark is surpassed, the causal connection with our solar system would be severed due to the relentless expansion of space itself. The expansion of the universe would simply outpace its capacity for retrograde motion. Nevertheless, we're not here to contemplate a return journey. Our purpose is to confront the original question: is it truly possible, with infinite acceleration, to reach the ultimate boundary of the universe? Let us fast forward. When the onboard clocks of our starship register 200 years of continuous flight, an almost incomprehensible span of 10 to the power of 41 years would have elapsed in the rest of the universe. At this unfathomable epoch, due to the accelerating expansion of space, it becomes almost certain that within the entire observable universe there would exist no other particles whatsoever apart from the starship itself. Our vessel would be traversing an absolute, unyielding cosmic darkness. At this extreme stage, the very concept of time dilation begins to lose its meaning. There is simply nothing left with which to compare the onboard chronometers. The starship would have become the sole, isolated locus where time, as we understand it, still exists. And the generations of astronauts born aboard this cosmic vessel, they would have no one to voice their profound, unspoken lament that they never, in fact, signed up for such a bleak and solitary destiny. The grim reality is that our starship, however persistent its acceleration, would never be able to reach any sort of spatial edge of the universe. This is due to the fundamental truth that distant regions of the universe are expanding away from us at velocities that exceed the speed of light. No matter how ferociously we accelerate, we would never even catch up with the edge of the observable universe, let alone the entirety of the universe itself. This, of course, was not the answer I'd been seeking. It left me with a sense of the insurmountable, an intimation of an ultimate, unbridgeable frontier. So, what then is cosmology? It is most certainly not what might first spring to mind. Cosmology stands apart, fundamentally distinct from all other branches of scientific inquiry. Typically, science involves disassembling phenomena into progressively smaller parts. Cosmology is the singular science that endeavours to achieve precisely the opposite. It strives to reassemble all the disparate pieces into a single cohesive picture. It concerns itself with the study of the universe, not merely galaxies and superclusters, but also the human being, with their profound capacity to understand and perceive this very universe. Every individual, whether they are migrating, participating in a revolution, or entering into a marital bond, is, whether consciously aware of it or not, profoundly influenced by their underlying beliefs about the universe. And this remains true, irrespective of whether we explicitly acknowledge it or not. What we implicitly believe, we simply perceive as unvarnished truth, that the world is simply this way. The expansive history of cosmology serves as a powerful testament to this. In every epoch, people have firmly believed they had, at long last, uncovered the true nature of the universe. Yet, each successive generation has invariably found itself merely crafting another sophisticated mask that temporarily fit the enigmatic face of an ultimately unfathomable cosmos. The profound question then arises: will we ever genuinely ascertain the true nature of the universe, or are we perpetually destined to merely believe that we know? If the universe in its deepest essence is not what it appears to be, then how can we even begin to search for its edge? Consider this. In the 12th century, the universe, as conceived by the German abbess Hildegard of Bingen, was depicted in a schema that, to our modern sensibilities, appears strikingly quaint. Since that distant era, we have undeniably advanced considerably. But will the people of 1,000 years hence gaze upon our current cosmological model with the same sense of historical distance with which we now regard the mystical geocentric model of a 12th century visionary? It is a humbling thought. You might, at this juncture, interject and inquire, but why do you assume that the universe, whatever its ultimate nature, possesses an edge at all? Perhaps it is in fact infinite. This argument is a venerable one, tracing its lineage back to the Greek philosopher Archytas. Archytas's famous paradox goes something like this. Imagine an individual standing at what they perceive to be the outermost boundary of the universe. What would then transpire if they were to throw a spear beyond this supposed limit? Would the spear recoil, deflected by an unseen barrier, or would it pass cleanly through? If it were to pass through, it would logically imply that something exists beyond that boundary. If it were to recoil, it would signify that it had encountered some limiting barrier. But then, the very existence of that barrier would itself necessitate something to limit it. This chain of reasoning, Archytas argued, extends infinitely. Therefore the universe must be infinite. For over 2 millennia, the most brilliant minds have grappled with this profound enigma. However, what the ancients did not grasp was a profound, counterintuitive truth. The universe can, in fact, be infinite, and yet simultaneously possess neither an edge nor a boundary in the conventional sense. It is common knowledge that the sum of the angles within any triangle amounts to 180 degrees. However, this is not entirely accurate in all contexts. As far back as the 19th century, the great mathematician Carl Friedrich Gauss began to harbour suspicions about this very axiom. To understand his insight, let us engage in another thought experiment. Imagine we are two-dimensional creatures dwelling on the surface of a spherical planet. In such a scenario, the surface of our planet would constitute our entire cosmos. If we were to inscribe a small triangle on the surface, we would indeed obtain the familiar sum of 180 degrees. However, if we were to construct a triangle of truly immense proportions, we would invariably discover that the sum of its angles would be greater than 180 degrees. Gauss hypothesized that our own three-dimensional space might similarly possess an inherent curvature. In such a curved space, he reasoned, the sum of the angles of a sufficiently large triangle would deviate from the Euclidean ideal. As far as we know, Gauss, working in secrecy, used geodetic instruments to measure a colossal triangle formed by 3 mountain peaks in Germany. He did observe a slight deviation, but it fell within the margins of experimental error. The reason for his secrecy was practical. A man of his stature attempting such a thing would have been perceived as pursuing an absurdity. Similarly, the brilliant mathematician Nikolai Lobachevsky faced severe professional ostracism for his pioneering work on non-Euclidean geometry. Ultimately, it was Albert Einstein's general theory of relativity that was rigorously validated by experiments. These revealed a startling truth. In the vicinity of massive objects like Earth, the angles of a large triangle could indeed sum to approximately 180.0002 degrees. This minute yet significant deviation must now be accounted for in applications like satellite navigation. In more extreme environments, like the regions surrounding black holes, the distortions are visible to our perceptive capacity, manifesting as seemingly impossible curvatures of light. The point I am building to is this: the universe, on its grandest scales, could theoretically curve back upon itself, much like the surface of a sphere. However, armed with increasingly precise technologies, scientists have meticulously measured the curvature of the cosmos. What they have consistently found is no discernible overall curvature. While space is locally curved, on the larger scales the universe appears to be flat. This empirical finding, if accurate, lends strong support to the notion of an infinite universe. The physicist Max Tegmark posits that the total number of all possible unique combinations of particles within our observable universe amounts to approximately 10 to the power of 10 to the power of 118. This is a number of truly colossal magnitude. But if the universe is, in fact, infinite, then this proposition leads to a mind-bending implication. It suggests that if you were to project a straight line from Earth, after traversing a distance equivalent to 10 to the power of 10 to the power of 118 times the diameter of the observable universe, that line would invariably intersect with an exact replica of Earth. On this distant, identical Earth, there would exist a duplicate of our observable universe, within which your precise copy would be engaged in the very same thoughts and actions that you're experiencing at this exact moment. While this might initially strike one as thrilling, the reality is that if the universe is infinite, it leads to a host of monstrous philosophical consequences. Trust me when I say that you would not, in the deepest sense, desire to inhabit an infinite universe. However, there are two crucial caveats. Firstly, the universe might indeed be a closed system, but its curvature might only manifest on truly gargantuan scales. Our current instruments, much like Gauss's, might simply be insufficiently sensitive. Our measurements only indicate that the universe is flat with an accuracy of approximately 99.75%. This implies that if it is not flat, it must be at least 400 times larger than the observable universe, rendering its curvature imperceptible to us. And secondly, the universe does not need to be curved to be a closed, finite system. Consider the surface of a cylinder. Geometrically, it is flat, because parallel lines drawn upon it will remain parallel indefinitely. Yet, it possesses a finite closed dimension in one direction. The same could apply to our universe. It could be flat, yet simultaneously a closed system. In a universe shaped like a four-dimensional torus, for instance, space would appear flat, yet if you were to travel in a perfectly straight line, you would, eventually and inevitably, return to your precise point of origin. This intricate exploration reinforced my conviction that the probability of ever physically reaching an edge of the universe is vanishingly small. But then, a new thought began to coalesce. Edward Harrison, in his insightful treatise, observes, "Space and time, in most universes of the past, were merely the stage upon which the cosmic drama was enacted. In the modern physical universe, however, space and time are the leading protagonists. If space and time are indeed so fundamental, if we conceive of space-time as the very interwoven fabric from which the universe is spun, then perhaps, to apprehend the edge, it would suffice to simply tear that fabric. Do you comprehend the audacious implication? We understand almost nothing about dark energy, that enigmatic force responsible for the accelerated expansion of space. It is dark energy that holds the potential to unleash a sudden, cataclysmic apocalypse, quite literally tearing apart the very texture of reality. Currently, it's believed that dark energy is not potent enough to tear apart gravitationally bound objects like galaxies. This, on the surface, provides a measure of reassurance. However, this holds true only if dark energy is not, in fact, something far more potent than our models suggest. A seminal article, co-authored by physicist Robert Caldwell, posits a chilling scenario. The epoch during which cosmic structures can exist might prove to be astonishingly brief. Dark energy, under certain conditions, could conceivably lead to a cataclysmic event that scientists term the Big Rip. How might such a scenario unfold? Initially, the largest cosmic structures would begin to unravel. The first ominous harbinger would be the gradual disappearance of galaxy clusters. Due to the finite speed of light, we would only become aware of this long after it had begun. The galaxies of the Virgo supercluster would begin to recede from our Milky Way at an ever-increasing velocity. Soon, the stars on the outer fringes of our own galaxy would scatter chaotically into the void. Our Milky Way would commence a slow, inexorable process of evaporation. The night sky would grow progressively darker. Approximately 7 months prior to the ultimate Big Rip, we would become aware of a subtle expansion of the orbits of planets in our solar system. Earth would drift from the Sun, our Moon would recede from Earth, our planet would plunge into a profound darkness and solitude. By this stage, any remaining structure would be subjected to an intense stretching. The upper layers of Earth's atmosphere would boil away. The tectonic plates would be thrust into tumultuous motion. Just 1 hour before the final cataclysm, the internal pressures would become unbearable, causing our planet to violently explode. Yet, a few intrepid individuals might theoretically survive this initial dissolution, having fled Earth aboard a specially designed rocket. But this reprieve would be agonizingly brief. Soon, the electromagnetic forces that hold together the atoms and molecules of the human body would no longer be able to resist the relentless expansion. The very molecules of their being would dissociate, and they would be torn apart from within. They would perish, never quite witnessing the ultimate moment. In the final, horrifying moments, roughly 10 to 20 seconds before the Big Rip itself, the atoms composing all matter would disintegrate, and then, at last, the very fabric of space-time would be rent asunder. No point, I mused. Firstly, humanity would perish long before perceiving the tearing of space-time, and secondly, this event, if it is to occur at all, is not predicted for several tens of billions of years. And what truly does the tearing of the fabric of space-time even signify? It remains a concept profoundly difficult to grasp, leaving me still searching for a more tangible edge. But since space is expanding, does it not necessarily expand into something? Perhaps into a higher dimensional space? If so, then what if the boundary of our universe passes directly through us, and we simply remain oblivious? What if our universe is but a part of something grander? If so, perhaps we could at least catch a fleeting glimpse of that higher realm. And indeed, the leading candidate for a theory of everything, M-theory, offers precisely such a framework. It posits that our universe is a brain, a membrane, with 3 spatial dimensions and 1 temporal dimension, existing within a larger hyperspace. This hyperspace, M-theory suggests, contains additional spatial dimensions, curled up in ways we cannot perceive. It sounds like science fiction, yet physicists take this theory with the utmost seriousness. According to M-theory, these additional dimensions are omnipresent. So, what prevents us from stepping into them? The very laws of physics, the atoms and subatomic particles that constitute our bodies, the electromagnetic fields, the nuclear forces, all these appear to be inextricably confined to our familiar 3 spatial dimensions. Every attempt to formulate how known matter might interact with extra dimensions has led to the conclusion that virtually all particles and forces are stuck here. There is, however, a singular and profound exception: gravity, and the associated curvatures of space-time. The peculiar leakage of gravity into these other dimensions is a theoretical mechanism that helps explain why gravity, in our dimensions, appears so incredibly weak. To illustrate, a weak refrigerator magnet can effortlessly defy the gravitational pull of an entire planet. This underscores gravity's relative feebleness. So, while gravity can, theoretically, traverse these dimensions, my hand, alas, cannot. However, it remains possible that other unknown types of matter or forces might exist that are capable of existing in more dimensions. In such a scenario, these exotic entities could potentially penetrate into our reality. Imagine a 2-dimensional universe, a flat plane, embedded within a 3-dimensional space. Within this 2D universe, a 2D inhabitant has sealed themselves in a room. Another 2D person on the outside would be unable to enter. Now introduce a 3-dimensional object, a cylinder. For this cylinder, there are no impediments to entering the 2D person's room. As it passes through their flat world, the 2D inhabitant would only observe its 2-dimensional cross-section, perhaps a circle or an ellipse. Now transpose this to our own 3-dimensional universe. It is conceivable that a 4-dimensional object could enter my home. How would such an event manifest? The precise nature of multi-dimensional phenomena remains beyond our direct apprehension. However, there is a reasonable hypothesis that we might never be able to directly perceive or experience them through our conventional senses. The cross-sections of such an entity might appear transparent or beyond our sensory input. However, there is one peculiar phenomenon we might detect. Recall that gravity is the sole force capable of propagating across all dimensions. Therefore, if an entity from hyperspace possessed a sufficiently strong gravitational pull, it would subtly bend the rays of light passing through it. This gravitational lensing would distort our perceived images of reality. Furthermore, if this entity were rotating, it could entrain the very space around it in a swirling motion. This frame-dragging effect could, in principle, be felt and observed. Our evolution has confined us to a three-dimensional world, rendering four-dimensional objects inherently counterintuitive. Yet, here is where things become fascinating. A remarkable study investigated the capacity of human beings to navigate a virtual four-dimensional maze. The experiment employed a specially designed game. The research unequivocally demonstrated that the mechanisms of spatial processing within the human brain are not rigidly constrained to 3 dimensions. After a brief period of training, individuals were surprisingly capable of orienting themselves in a 4-dimensional environment. The human brain is a remarkably flexible instrument. What is even more astonishing is that, according to M theory, hyperspace might contain a multitude of other universes, and these other universes are not necessarily confined to some impossibly distant realm. It is theorized that higher dimensions could influence our universe in subtle ways, though our current technologies cannot yet measure these influences. In any case, this particular avenue of exploration, while tantalizing, ultimately presented a similar dead end. What utility are all these additional dimensions if one can only be entered from them into our own, and not the other way around? Perhaps one of the most central insights that Edward Harrison conveys in his book is this: regardless of whether future experiments confirm M theory or not, it will fundamentally remain a model. It will be yet another conceptual framework through which we attempt to apprehend reality. This is because, for every individual, the concept of the universe is inherently subjective. For those inclined towards religious faith, the universe is a divinely crafted realm. For artists, it is a world of exquisite sensitivity. For philosophers, it is a complex tapestry of logical structures. And for scientists, it is a meticulously observed world. And for each of these perspectives, their particular model can be perceived as the true universe. Consider the Ptolemaic model. Ptolemy devised a geocentric model with a stationary Earth. This model provided a remarkably accurate explanation for the observable movements of the planets. For over 1,000 years, people lived within a universe where the sun, moon, and stars revolved around the Earth, and this model functioned admirably. Then, in the year 1500, Nicholas Copernicus presented his mathematical model of a heliocentric system. Interestingly, his initial model described the movements of the planets less accurately than Ptolemy's system. Today, the Copernican principle asserts the mediocrity of Earth's position. Yet, Copernicus himself placed the Sun in the centre of a finite universe, bounded by a solid sphere of fixed stars. Later, Johannes Kepler, enraptured by Copernicus's idea, meticulously refined the model, driven by a blend of scientific rigour and theological conviction. Do you know why? Kepler considered the Sun to be analogous to God the Father, and thus it had to reside at the centre. The sphere of fixed stars represented the Sun, and the space between them, the Holy Spirit. His seminal work, Mysterium Cosmographicum, even included a chapter reconciling the Sun's central position with biblical passages. Modern astronomy owes a considerable debt to these very books. Edward Harrison argues that every society constructs its own picture of the world. This collective cosmology is like a finely crafted mask placed upon the face of the unknown universe. Our contemporary era is not merely characterized by different models of a single universe, but by a proliferation of different universes within various cosmological models. Consider again M theory, where our universe is a brain within a hyperspace. This implies the existence of other brains, each a distinct universe. In models of eternal inflation, there are an infinite multitude of universes. In the model proposed by Lee Smolin, new universes are perpetually born within black holes. Therefore, Harrison argues, when we use the grand word universe with a capital U, it inadvertently conveys the impression that we have definitively captured the ultimate nature of existence. By designating our current model as the universe, we overlook the humbling truth that this model is destined to meet a similar fate as all its predecessors. We frequently commit the error of mistaking the mask for the face. Our ancestors consistently made this mistake, and our descendants will, in all likelihood, perceive us repeating it. Since we are fundamentally incapable of truly apprehending the ultimate nature of the universe, we can, as Harrison suggests, humbly circumvent such presumptive claims by using a more modest term, universe, with a small u. This linguistic distinction serves as a potent reminder of the inherent limitations of our understanding. But then, one might reasonably ask, could there not eventually come a moment when we truly comprehend everything? From Harrison's perspective, the answer is a resounding no, and it is this assertion that guides us toward the ultimate understanding of my initial question. The edge of the universe, he proposes, is not merely spatial, it is also temporal. The universe had a definitive beginning in the singularity of the Big Bang and thus possesses a time-like edge at its genesis. If this universe were to recollapse into a big crunch, it would possess two such edges, a beginning and an end. These temporal boundaries are not solid cliffs, but a gradual dissolution. Since time itself is a physical dimension, it cannot extend beyond the confines of the physical universe. The very problem of cosmological singularities is one of the most formidable challenges in physics. The crux of the issue is this: absolutely none of our knowledge about events after the Big Bang can furnish us with any meaningful information about what occurred before it. All logical extrapolation and causal reasoning utterly break down when we attempt to apply them to singularities, and conversely, nothing that occurs before a Big Crunch singularity can provide any information about what will happen after it. These are points where the fundamental laws of cause and effect are violated. It is conceivable that the physical world simply dissolves at these initial and terminal points into a chaotic, disordered metric foam. But in truth, our understanding of these boundaries remains woefully inadequate. Perhaps this stems from our equally poor comprehension of time itself. But then, another thought occurred to me. We need not await the ultimate end of time. The Big Bang and Big Crunch are not the sole locations where we might glimpse the boundary of space-time. In fact, we might be able to achieve this relatively nearby. As early as the groundbreaking work of Roger Penrose, it was demonstrated that when a dying star collapses, a singularity must inevitably form. This represents a region where space and time themselves approach a definitive end. Thus, all we theoretically require is a single black hole and a copy of a particular book by Kip Thorne. Kip Thorne is the brilliant mind behind the scientific conceptualization of the film Interstellar. Beyond that, he is one of the world's foremost authorities on Einstein's theory of relativity and a Nobel Prize recipient. His book, Black Holes and Time Warps, Einstein's Outrageous Legacy, is a monumental work. If one were seeking accessible yet profound information about these enigmatic entities, this would be the definitive source. So strictly speaking, black holes are regions of space where the forces are so extreme as to be fatal. A singularity is a region where the curvature of space-time becomes infinitely large, and space-time itself effectively ceases to exist. This, it seemed to me, was precisely what I had been searching for. Let us then finally confront this profound edge, utilizing the mask of the universe known as general relativity. Friends, at this point I require your absolute undivided attention. This particular segment is intricate, but if you can navigate it, you will likely gain an understanding of the deepest mechanics within black holes that few ever acquire. In the film Interstellar, the character Cooper never actually entered the singularity, as he was retrieved by the Tesseract just before. Here, however, we shall delve into the harrowing events unfolding within the singularity, the very point where the space-time continuum terminates. A black hole is a region where gravity is so powerful that space-time literally folds back upon itself, sealing off all pathways of escape. Imagine an astronaut, feet first, falling into one. A small black hole would be unsuitable. Its tidal forces would violently rip the astronaut apart long before they crossed the event horizon. However, if the black hole is truly massive, the scenario is different. At the heart of our galaxy resides Sagittarius A, with a mass exceeding 4 million suns. Such a colossal entity would suit our purposes. The larger the black hole, the longer an astronaut could survive. In a black hole with a mass of 10 billion suns, an astronaut, having crossed the event horizon, would fall for several hours, experiencing no discomfort. It would be only in the final second before reaching the singularity that they would perceive a terrifying phenomenon. Their legs and heads stretched immeasurably, their torsos simultaneously compressed. In the fleeting hundredths of a second preceding the singularity, these forces would become so intense that the body would yield, leading to the astronaut's inevitable demise. When the remnants of the body reach the singularity, the stretching and compression of space become infinitely large. According to general relativity, the astronaut effectively merges with the singularity, becoming an inseparable part of its infinite density. They cannot pass through, because a singularity possesses no other side. Space and time cease their coherent existence. If we conceptualize the space-time of a black hole as a sheet of paper, the singularity would be its razor-sharp edge. However, unlike a sheet of paper, nothing that enters a singularity can ever return. Everything that falls into it is instantaneously annihilated in its classical form. But here lies a crucial caveat. Thorne meticulously explains that this illustration disregards the profound curvature of space. In reality, when the astronaut's body reaches the singularity, it is not merely stretched delicately. It is stretched lengthwise to an infinite extent, while simultaneously being compressed laterally to a size of absolute zero. How one might envision this defies conventional intuition. This is where common sense fails. Of course, it is not only the astronaut who experiences this. All forms of matter are subjected to this infinite stretching and compression. This all sounds dramatically captivating, yet profoundly implausible. For while infinities are acceptable in mathematics, their appearance in physical reality almost invariably signals a breakdown in our understanding. Physicists harbour deep skepticism whenever their equations yield infinities. The infinities within a singularity are no exception. It is here that the laws of quantum mechanics enter the fray. They simply do not concur with such a cataclysmic infinite outcome. Thorne clarifies that quantum mechanics fundamentally prohibits the existence of all forms of true infinities. Extremely close to the singularity, a momentous convergence occurs. The laws of quantum mechanics merge with the laws of general relativity, transforming the rules. These new principles are termed the laws of quantum gravity. Quantum gravity comes into effect when the fluctuations of the tidal forces become so immense that they utterly deform all objects. This occurs at an unfathomably brief temporal scale, approximately 10 to the power of minus 43 seconds. The forces are unbelievably savage, but the fluctuations are still demonstrably not infinite. By this point, the astronaut is assuredly dead, their body parts commingled, yet crucially, nothing is truly infinite. The game continues, and it is at this juncture that quantum gravity radically alters the very nature of space-time. My vision is not what it once was, so I have reread this passage multiple times. Are you ready? Quantum gravity, it is theorized, tears apart the very connection between space and time. It literally pries them apart. Subsequently, it fundamentally destroys time as a coherent concept. And it obliterates the very definiteness of space. Time simply ceases to exist. We can no longer meaningfully assert that this happened before that, because without time, the concepts of before and after are rendered meaningless. Space transmutes into a probabilistic foam, a frothing, chaotic sea of possibilities. A brief respite and then a direct quotation from Kip Thorne. Before the rip, meaning outside the singularity, space-time resembles a piece of wood saturated with water. In this analogy, the wood represents space and the water represents time. Both are tightly intertwined and unified. Within the singularity, however, the laws of quantum gravity are akin to fire thrown upon such a damp piece of wood. The fire evaporates the water from the wood, and the wood is left alone and unprotected. Similarly, within the singularity, quantum gravity destroys time, and space remains alone and unprotected. Then, Thorne continues, the fire transforms the wood into a foam of flakes and ash. In an analogous fashion, the laws of quantum gravity transform space into a random probabilistic foam. It is precisely this random probabilistic foam that constitutes the singularity. Within this foam, space possesses no singular definite form. It exhibits no fixed curvature, nor even a stable topology. Instead, there exists only a probability for this or that curvature, for this or that topology. For example, there might exist a 0.1% probability that the curvature assumes a particular form, a 0.4% probability that it takes another, a 0.02% probability for a third, and so on. Do you comprehend the implication? This does not mean that space spends a percentage of its time in any form, because within the singularity there is no time. The only question that retains any meaning is, what is the probability that space possesses form A, B, or C? My mind reels with the sheer audacity of this concept, because this, in essence, is what the boundary of the universe looks like, at least according to the limits of my current search. It feels like something, a tangible, albeit utterly abstract conclusion. I am at a loss to visualize such a state. But this is the profound utility of mathematics. It allows us to explore concepts that lie beyond the grasp of the human imagination. And this is one of the ultimate capabilities of modern cosmology. It enables us to investigate the literally unimaginable. You might object. Even if this holds true, no astronaut would ever perceive this boundary. You yourself stated they would be torn to shreds beforehand, and this observation is entirely accurate. However, there's another fascinating twist. As detailed in calculations from 1991 by Werner Israel, Eric Poisson, and Amos Ori, this will sound incredibly counterintuitive. The chaotic tidal forces within a black hole actually weaken over time. Allow me to elaborate. If a colossal black hole were newly formed, an astronaut falling into it would be violently ripped apart. But if one were to judiciously wait for several years, then by that time, the tidal forces of the singularity would have become so gentle that an astronaut could pass through them without any discernible discomfort. The astronaut would, theoretically, reach the very edge of the probabilistic singularity almost entirely unharmed. And it is only at the very precipice of this singularity, when the astronaut is face to face with the ultimate laws of quantum gravity, that we enter a realm of profound uncertainty. We genuinely have no concept of whether they would perish or survive, because our understanding of the laws of quantum gravity remains profoundly incomplete. You might argue, very well, but you have cleverly substituted the boundary of the universe with the boundary of space-time, and you are correct. Yet what could be more foundational than space-time itself? On one hand, it seems impossible for a finite universe to exist beyond which there is absolutely nothing, and it is plausible that our universe has something external to it, and might also be infinite. But on the other hand, the elegant simplicity of mathematics does not demand anything external. From a third and most crucial perspective, everything hinges upon how we define the universe. If it signifies all things that can possibly exist, then by definition, there can be nothing outside it. For anything we might conceive of as residing outside, even absolute nothingness is by its very nature still an existing entity, and thus part of the universe. We cannot embark on a journey to the edge as Dante and Beatrice did, to gaze upon the entire universe from some celestial tribune. But what underpins Harrison's certainty that we will always operate solely with models? On one hand, it stems from the inherent limitations of the scientific method. No theory can ever be definitively proven, only falsified. But Harrison's primary argument delves far deeper. Modern scientific cosmology investigates a universe that explicitly includes all that is physical and excludes all that is non-physical. What constitutes the physical? Everything amenable to measurement. Atoms and galaxies, cells and stars. But there is something else. We, as physical beings, are contained within this physical universe. And yes, the physical universe has been astonishingly successful in explaining phenomena. However, it is fundamentally incapable of explaining mental phenomena, like consciousness. These subjective experiences are not directly amenable to measurement. An individual who persistently inquires, where precisely is the mind located, would find themselves on a circuitous path. Biologists might assert that mind is an emergent manifestation of complex physical systems. If this fails to satisfy, they might direct the inquirer to psychologists. But no two psychologists would furnish an identical answer. Some might then direct the inquirer to physicists. Yet, physicists might either deny the existence of the problem or politely recommend a return to the biologists. In desperation, the inquirer might consult cosmologists. For if others can deflect this enigma, cosmologists study the entire universe, and the enigma of consciousness stares them directly in the face. What would Edward Harrison himself respond? Consider the evocative painting by M.C. Escher, a self-portrait. The artist depicts himself within a reflective sphere, holding the very sphere in which he is reflected and so on, in an infinite regression. This is a powerful demonstration of infinite regress, a potent challenge to any theory that leads to this endless loop. The assertion that everything has a cause leads directly to an infinite regress. Thus, if we acknowledge the logical force of this argument, we are compelled to concede that the statement everything has a cause is ultimately absurd. Cosmology, Harrison argues, is fundamentally incomplete because we consistently fail to place ourselves, the cosmologists, within our own models. The universe, in its entirety, possesses self-awareness, for it contains us. Yet, the physical universe, as described by our models, possesses no self-awareness. We can assign our bodies and brains to the physical universe, which is but a model. But we cannot, without falling into an infinite loop, assign our consciousness to a universe that is comprehensible by our consciousness. If we attempt to do so, we enter an endless cycle. Cosmologists study the universe. There are cosmologists who study their universe, which contains cosmologists, and so on. Where, within the universe, is the rightful place for the cosmologist studying that universe? To resolve this, it's imperative to distinguish between the ultimately incomprehensible universe, of which we are a part, and our comprehensible universes, with a small u, of which we are not a part. Harrison poignantly states that it is particularly noteworthy that no physical experiment can definitively determine whether an object possesses consciousness. If an object is before me, I know with certainty that I possess consciousness, but by no physical instrument can I empirically prove that you do. Consciousness is not, it seems, a property measurable within the physical world. Some scientists postulate that consciousness simply does not exist. For my part, I'm not yet prepared to concur. More time is required. But with what I absolutely unequivocally agree is this. Almost certainly the universes of the future will differ significantly from our current vision. However, all of them will remain anthropomorphic. As the ancient Greek philosopher Protagoras asserted, man is the measure of all things. How human beings think ultimately determines how they understand their universe. Of course, the universe itself was not created by humanity, but we possess no truly verifiable, unvarnished concept of what it actually is. All we truly know is that it contains us, the creators of these myriad universes. Modern cosmology deals exclusively with a physical model of the universe. This, Harrison reminds us, is yet another mask. But what a truly magnificent, awe-inspiring mask it is. In its crafting, the entire inventive genius of the greatest thinkers has been poured. Is it any wonder that many, when confronted with the sheer majesty of the physical universe, erroneously mistake this newest, most sophisticated mask for the genuine face? If you still harbour skepticism, what will you make of the following revelation? Presently, the physicist Nima Arkani Hamed is developing a revolutionary method for calculating particle interactions. This approach is entirely novel and does not take into account the concepts of space or time. Already examples of physical systems remarkably similar to those we observe are emerging, systems that can be described without any reference to space-time or even quantum mechanics. One might be tempted to dismiss this, but this is not an isolated thought. Clifford Johnson, a professor at the University of Southern California, echoes a similar sentiment. I think we're all coming to a better understanding of one of the ideas from string theory, which is that space-time is not fundamental. Sean Carroll, a cosmologist at Caltech, agrees. Space-time is real, but it's not fundamental, just as wet is real, but not fundamental. It's just a higher-level emergent description. The implications are staggering. The discussion is not about whether space-time exists. It undoubtedly does. However, at a more profound underlying level, it would manifest as something entirely, unimaginably different. And so, tell me, in such an elusive and shifting landscape of understanding, how can one possibly seek the edge of the universe if even that which appears so utterly fundamental, space and time themselves, might ultimately prove to be but another sophisticated mask, another emergent property of a deeper, more enigmatic reality? Are you still here? Given the inherent complexity of the material we have explored, I truly take my hat off to you. Perhaps, of course, it is only to me that these concepts seem so intricate. But in any case, thank you for embarking on this intellectual journey with me. As the cosmic hum gently fades and the echoes of these grand questions recede, may you find comfort and peace in the quiet vastness of your own thoughts, drifting now towards the deep, rejuvenating embrace of sleep.